I'm starting the live stream, I think. Hello again. This is going to be some chill maths on twitch.tv/JamesVanRowe. I'm pretty sure I'm live and I've unmuted and stuff like that. Those are all the things I'm supposed to do. I missed a week last week, so devastating for regularity. So the one thing people say, if you want to do a live stream, you've got to be periodic function. You've got to do it at the same time every day, every week, every hour, whatever you're doing. But I've got a cup of tea and I've got some maths. So we're going to be all right. My tags are mathematics, maths, math, English. I can't remember why I put English on there. I think you're supposed to have a language one. We're not going to talk about English literature. Hello, Herb. Nice to see you again. Welcome back to the stream. It's more of these, whatever these are, symmetries of the fairy diagram. Hi, Mary. Good to see you too. I think if we do well enough here, we're going to be turning continued fractions inside out and reversing all the numbers and understanding, getting some relationships between these numbers, their rational approximations and their positions in this big diagram that we've got. I remember last time we talked about this, there was some stuff about Mobius transformations, all of that jazz. That's the plan. No particular goal in terms of viewers or pages or maths. Although I do notice that I have hit a 75. I think there's a little thing in Twitch that says I've got to 75% there. So who knows? We might have to actually edit that Wikipedia page or whatever it is when we get to that goal. So the only goal is slowly learning maths. Mary's not well. Sorry to hear that, Mary. And hello to maths2222222. A funny thing to do if you're anonymous in chat or if you're watching on Twitch without a username, a funny thing to do would be to register maths22222222 with 8 2s instead of 7, because then I'll find it very, very confusing. That would be an excellent troll, I think. Sort of thing that I'm sure that happens to other streamers, that people have just got like really confusingly similar usernames that they have to read very carefully in order to follow chat. You can set your colour at customize as well. Right, so when I'm not encouraging viewers to impersonate each other, what am I up to? Oh, I don't know any R, I can't help Herb. Sorry R, and sorry Herb. Right, okay. Yeah, sending Twitch hearts. Good. Here we go. You are become the R to defeat the R. It's the only way. Right. Okay. I've got a cup of tea. If you don't already have a cup of tea, you might like to get a cup of tea because nothing's going to happen very quickly. Right. Okay. What have we got? Linear fractional transformations, which is what we're calling in this book that we're reading. Transformations of the fairy diagram that kind of send the circle to the circle or send the upper half plane to the upper half plane and send rationals to rationals. And I've convinced myself, I think last time, that those are what I have previously met as Mobius maps. Okay, I've got through 3 words. I'm doing great. 3 words I'd seen before. I am here. Ooh. It can be used to compute the values of periodic or eventually periodic continued fractions. Have we seen that? What was going on there? No, there's some. Yep, back up. Oh, what we were going to do n times or something. What on earth was this? We had some symmetries. I remember the symmetries. Oh, and some of the symmetries were translations. And we've interpreted that previously there was a big long string of matrices that was building the coefficients of the numbers that appear in continued fraction, and now we're doing, yeah, and now we're saying, okay, that's generating the continued fraction. Realizing what you don't know is the important but humbling bit of learning, which is it is much more easy and comfortable to just pretend that you know everything, and it's easy to stay in that state. You just have to not listen to anything and not experience anything, and then you'll be able to convince yourself that you already know everything. Definitely some people have achieved this. The much harder thing to do is to look directly at things you don't understand, which I guess I'm taking the easy out by picking something that doesn't really matter, like continued fractions. Right, yeah, Google, let's go. Maybe I should just Google this instead of reading a book. It'll give me an AI summary as well now, that's like a book. Oh my goodness, right. So, the periodic or eventually periodic infinite continued fractions. We think there's a relationship between those and symmetries. Because something like, if you do the symmetry, and then it still looks the same. What still looks the same, James? Always. Yeah, I've just reread the sentence, and it actually says that this is what's going to happen in this section. So I should be looking forwards, not backwards. Here we go. Let's go. Right, it doesn't say we've already done this. It says we're about to do it. Reading is hard. Why have I got English in my tags? Am I certain that I speak English? Right, okay, can be used to claim about what we're going to do. To illustrate this, here we go. Consider the periodic continued fraction, this one. The associated periodic strip in the Fourier diagram can be extended. I'll pretend that that was a good sort of learning moment where you think about what's about to happen. We've done that before. Give an infinite strip that's periodic in both directions. Right, so this is the kind of repeating section. This is describing the fraction 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 2 plus 1 over... Oh, no, there's a 1 in there as well. 3, 1, 4. 1 plus 1 over 4 plus 1 over 2. But confusingly, we're going to imagine this going both ways. What on earth does that mean? So that means something like the numbers we see along the way here, along this path, those are the... Well, I'd normally have to call them convergents, but let's steer away from that language. If you work this out from the bottom, which is a strange thing to do because it's infinitely long in that way, but you sort of hope that those things don't matter too much. You could calculate going upwards. So sort of if you stop here, then you have a kind of challenge to calculate what 1 over 3 plus 1 over 4 plus 1 over 3 plus 1 over 1 plus 1 over 4 plus 1 over 2 plus so on, and then repeating. You have a challenge to work out what that is. And then once you've worked out that number, including all of the repeatingness down that direction, you could then do 1 over 2 plus some stuff on the front. And it feels like that should be a periodic sequence because it should come back round again. Why is this an infinite thing? Why doesn't it just loop back round again? There's this roll of 1 over 0 in the middle of this picture. So sort of after you've calculated 4 of these things, if I set you this challenge of like forget all the stuff on the left, starting at 1 plus 1 over, starting at 1 over 3, let's say, calculate that thing. That's a challenge that you can do. I've set that challenge to children before, by getting them to do sums like x is 1 over 1 plus x. It does it again down here. You can put different numbers here and you get different things. This is longer because it has 4 numbers in it, but you can calculate these things. We're going to see that that is quadratic equations, which is why I can give that exercise to children. But I'm interested in the idea that we're going to get an infinite strip in both directions, because that suggests to me that we're going to generate, and I briefly thought there would be larger numbers over here on the left. And I suppose 1 over 0 is a pretty big number. What's to the left of that? Now, how do I work this out? Can I remember the rule here? So 0 over 1 added twice. So why has this gone to infinity? What's going on? I really thought these were convergents. No, the whole thing overall is an irrational number that lives somewhere over here, in between, underneath all of these. These lines are sort of topologically, they're these semicircles that we've drawn before. They've been bent round to be straight lines in this strip as we go inwards towards some point on the real line. I'm imagining the upper half plane model with all the semicircles in, where we're zooming in towards some point. We've had some Desmos activities where you could zoom in underneath all of these nested semicircles. And the thing that matters is the pattern of whether the semicircles are coming from one side or the other. Said terribly. Let's have another go. There's a point maybe on the left where the semicircle is coming from, and maybe several in a row come from that point. and then at some point they're coming from a point on the right. So if you stand at this end and look up at this picture, you see something a bit like this upper half plane model that we've had with all these semicircles above you, where you see this kind of fanning sort of shape of semicircles coming out this way, and then at some point semicircles coming in this way, maybe quite a lot of them, and then some semicircles springing out from that point. If you stand underneath it and look up, then you see this kind of pattern of a route down to this point, joining ones where it changes direction, and in between several extra semicircles fanning around. I've drawn that picture quite badly, but I talked while I was doing it, so I think I've brought that back. I'm trying to also remind myself of how these diagrams work. What does this mean? What are all of these lines? I wonder if it's going to matter that this is an even number of numbers, so the thing repeats the same way up. Maybe that's not going to matter. So, okay, so the big sum is the actual irrational number at the end of the rainbow. We're not going to get to the irrational number at the end of the rainbow. We're going to generate lots of rational numbers along the way that are close numerically, surprisingly close. There's a rule for these, which is to add numerators and denominators separately, which makes me think they're a bit like vectors, but never mind. So here, 1 over 2, 3 over 7, let's write down 4 over 9. And then to get to this next one, you add, what do? You add 4 over 9, like a vector, to 3 over 7, 1, 2, 3, 4 times. So you get here, you add 4 over 9, and you get, or am I awake enough to add 9s together? Let's find out. 25, and then you add 4 over 9, and you get 15 over 34, and then you add 4 over 9, and you get 19 over 43. Oh, good. Okay. So you keep adding and you get these things. So working backwards, what do we get? So working backwards. So is this 3 over 7? Right, that's not the thing that I've been talking about with this kind of challenge for children where you add together all of this infinitely many fractions. Sorry, that sounds stupid, doesn't it? But it is a challenge I've set to kids on a summer school. Go and add together all of these infinitely many fractions for me. It keeps them busy. It's a good trick. Children yearn for adding together infinitely many fractions. This is what they want more than anything else. What am I talking about? We've added some numbers over here, haven't we? 1, 2, and adding 2's downstairs. 3, 5. Let's go back to 0 over 1. What was I expecting? I was expecting loop. It's kind of 4. Infinite strip is periodic in both directions. I think this is going to relate to 4 different irrational numbers, depending on where you start. You see this infinite repeating thing. Or maybe I'm overthinking it, and maybe you just draw the triangles and see what the triangles do. Draw the triangles, right, and see what the triangles do. Just can continue the pattern. So we'd like to find a linear fractional transformation of the things az plus b over cz plus d. That gives a rightward translation of this strip to do the thing that it is, which is periodic. And maybe the flipping is going to matter here if we're thinking about glide reflections are going to be the flippy ones. That's what a glide reflection is, I think. Translate and flip. The only possibility, stream is tagged English, let's do our best, is the transformation with matrix, and then some numbers have come out of nowhere. I guess this gets us to 19 over 43, 4 over 9, since this sends the original edge with the arrow on to this edge. And it's orientation preserving since the matrix has determinant 1, which is something we talked about before, that I didn't find very exciting, but still. Gives us an interesting pair of numbers, right? 4 times 43 and 9 times 19 only differ by 1. That's a property of these matrices in this textbook, that most of them have determinant 1 or -1, so you have this kind of large pair of integers that multiply to similar large numbers. 4 times 43 is pretty similar to 9 times 19. It's just a sort of pattern that we've got going on today. That's 172, right? And this is going to be 90 and 81 is 171. Ah, we're learning English. Oh, I'm really sorry to hear that. There's so many I think lots of the words I use are a bit weird. Yesterday I said fleckled, and somebody pointed out to me that fleckled is not an actual word, that I have to choose a lane. I have to either say flecked or speckled. And I found that irritating because I thought fleckled was exactly what I meant. English is quite nice normally for just letting people make up extra words. We've got words from absolutely everywhere, so why not add a few more in? Fleckled, like little flecks. But they said no. In English we say speckled or we say flecked. Little flecks. It's fancy ice cream. I saw some fancy ice cream. Right. Learning. Ooh, what's an eggcorn? Wait, is an eggcorn a word that's not a word? Eggcorn, a word or phrase that results from mishearing or misinterpretation of another. Oh, like instead of acorn, eggcorn. Fair enough. That sort of makes sense, doesn't it? Eggcorn. I like that a lot. Skewb for powers of 6. Ooh. See, that also makes me feel things, which... Good. Skewb. Actually, I've considered some alternatives, and skewb is quite a bit better than the alternatives. Right, good. Okay. Learning. Right. Oh my goodness, I've just read the next line. Here we go. This inequality can be verified either by calculation or by visualizing. Oh, right, okay. How the strip lies in the circular fairy diagram. There are some semicircles around in a big circle. Ooh. Plot the strip to the right of the edge 1001 lying in the upper half of the diagram. In the right direction to get to whatever irrational number we're going to. Oh, right. It really does translate the strip along itself. We can argue as follows. Label the 10 triangles. Oh, goodness me. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 triangles. Okay. T1 to T10. Continue this labeling with the subsequent triangles. The next 10 on the right. Oh my goodness. Oh, and then add one vertex at a time, and it's going to be okay. This is like induction or something, right? Add a vertex. The vertex are added. Vertices are added by a very particular rule, which is secretly matrix multiplication. So if you multiply by a big matrix, then it's going to be okay. Or if the matrices commute or something, and I should write stuff down when I say things like that. A bit hand-washy, yes. Wishy-washy, hand-wavy, yes. Hand-washy is also like, this proof's not very good, but it's not my problem anymore. Over to you to fix this. This proof is very hand-washy. Okay, good. Right, since T is alright. Yeah, I haven't understood why the map takes. If you convince me that the map takes V1 to whatever V11 or something, build the part of the strip to the right of the edge by starting with this edge and first adding V1 just to the right of 10 to form triangle T1. V1. We've got to decide where that is. We've got the mediant rule for adding. It's going to be at 1, 1. Then adding V2 to form T2 and so on. Yep, that's how the strip is built out of triangles. Since T is orientation preserving and takes this to this, takes the edge to the edge. Oh, this edge has got 2 triangles next to it, one on either side, and orientation preserving means you get the correct triangle? Yeah, we're exploiting the fact that these lines in the fairy diagram aren't just random, they form triangles. And each edge has a triangle in each side. So if you strongly believe that you've mapped this edge to that edge, then you check you've got the sides right, and then you can be pretty sure that you've sent this triangle, which is the triangle on the side of that edge. You've sent it to this triangle here. So there is a vertex, a third vertex on that triangle, and the argument is going to be that that's uniquely defined in both cases. And because the map is preserving edges, it sent those edges somewhere. Don't love this. So they intersect at a single vertex? I think they're not random, they're kind of special edges. Out of all of the edges that go through 0, 1, and there are many, you have sent it to this one. over here, because the map sends triangles to triangles. Are there other triangles that share that edge? I think the answer is no. No, yes, right? There's loads. Like, what on earth is this? No, there's only... You can't make a triangle out of weird edges that are miles away, can you? Can you? I've said it's only on two... I've said this edge is only on two triangles. This small one down here and that one up there. But, I mean, in this picture, sure. But are there other weird triangles that share that edge? You know, that have the edges going weirdly curving around here and coming back again? I think probably not. Not for geometry reasons, because the sides are all curved. But I think for fairy diagram reasons. Let's think about that. I drink some tea and think. How do I know that the triangle... So you've got a triangle with curved edges, let's say. You've got one edge you're really interested in. And there's exactly two solutions, we claim, for a number such that you get a little triangle like this that's connected to both of them. There are two solutions for numbers that are connected to both. Let's maths that. So if these are a over b and c over d, the connections would be sort of x over y. And the claim is that there are exactly two solutions for xy such that they're connected to both, such that a, b, x, y determinant is plus or minus 1, and that the determinant of connected over here is also a determinant fact, plus or minus 1. So that one is ay minus bx equals plus or minus 1, and this one is cy minus dx equals plus or minus 1. And with, we know that AD minus BC is plus or minus 1. I should maybe get my orientations worked out. I think with that loss of generality, 1. Because if it's minus 1, just swap which 2 points we're talking about. Now we've got this question about this triangle. Okay, this seems like a thing I can try and solve, right, down the margin. I've got this fact about A, B, C, and D, and I would like to work out, to convince myself that there are almost 2 solutions to these problems, and they look quite, I was going to say bazooty. No, aren't these problems quite weak to adding a multiple of the... Aren't these solutions quite weak to... so that first equation with the a's and b's in, I know there are loads of solutions to that. You can add on, where you can add b to y and you can add a to x, and it'll still be plus or minus 1, because it's plus ab if I add b to y, and minus ab if I add a to x. And I suppose possibly the point is going to be that if I add a to y, if I add b to y and add a to x, then the lower equation goes up by cb minus ad, which is non-zero, is 1. So now I'm in trouble. So that seems pretty plausible, actually, that there would be a unique solution. So, okay, we're getting there. Yeah, okay. So, if ay minus bx is 1, then find solutions. AB, these are in lowest terms, there are fractions. In lowest terms, so highest common factor 1. Find solutions, some sort of like Euclid Bezout sort of nonsense, or possibly fairy diagram things. Sorry, bad habit. I tend to, when I'm problem solving, I tend to revert back to whatever the first way I learnt material was, rather than engaging properly with the new way of doing things. I'm probably supposed to say semicircle a lot here, sorry. Find solutions with like Bezout or something, but then exactly one of those, at most one? No, because you can use the plus b. So the solutions are y is something, I don't really care what, there's some particular solution. Yeah, no, I really don't care what. And then you can add any multiple of b here, and you can, so long as you subtract a corresponding multiple of a over here, and then they work in this equation like this. And then exactly one of those, because I'll have, when you plug those into the second equation, in the second equation, I guess exactly two values of n work to get plus or minus 1, because incrementing n changes the thing by -1 or something. So if you go up, if you increase n, then you get an extra BC minus AD, so it increases this number, and I want plus or minus 1. So it looks like I get two solutions there, which makes me slightly nervous, because I have some degeneracy that I've just thought of that we'll get to. So then also solve AY minus BX, so also linked to this if. I suppose that should be or. Solve the -1 case, but the -1 case is just going to have negative of the solutions that I just found. Negative of the solutions I just found for x and y, even after I fixed this thing. So I'm going to find this. I'm going to recover the same solutions with minus signs for x and y. Or said differently, it might look like I found 4 points, but actually that's only 2 points, because minus x over minus y is the same number as x over y. That's the degeneracy. This fact that you can put minus signs upstairs and downstairs in your fraction. Even if you decided they have highest common factor 1, you still have this kind of units problem where ones and minus ones are always going to be around. Ooh, there's a pedantic way of talking about fractions. So when you say in lowest terms, you mean there is no non-trivial number that divides both the top and bottom, because it's true, of course, that 1 divides top and bottom, and also, I might forget this, but it could be true that -1 divides top and bottom. Wait, no, that's always true. It's always true that -1 divides top and bottom. Right, Brill, I actually looked at the live stream while I said that to get so that I could see in real time myself saying something stupid with stream lag. If I want to take something back immediately, but it hasn't quite. I could have like a sort of stream delay. This would be the technology, wouldn't it? Stream delay, and I get to sort of scrub it, not for like accidentally swearing or doing something bad, but like if I say something stupid, just haha, those 10 seconds didn't exist. Retract. So from you watching at home, it sort of occasionally jumps 10 seconds into the future and me apologising a lot. And then I have to build up the buffer again through ad breaks or inserting stuff to win the time back. Right, great. That's probably what they do on the radio, I'm sure. Yeah, this is what they do on the radio. A button to press where, like, if somebody accidentally divides by 0, then you can like, oh, never happened. Jump straight back in. Oops. I kind of want to set that up now. Although it'll only be funny for me. It'll only be funny for me because it'll sort of taking away 10 seconds of content. Right, okay, I've convinced myself of something fun, that there are exactly 2 points. A sort of +1 and a -1 solution. Doesn't make sense, that's the side. Which side of the triangle are you on? Okay, so exactly 2 points. So this is good news. It says if you've got an edge, you're sending edges to edges, and you're interested in that triangle, then as long as you're sending edges to edges, those edges are going to go somewhere, the point's going to go somewhere, and later on, over in this diagram, we've got a strong opinion that there should be some point here. Yeah, it's going to be the same point. I've convinced myself anyway. Right, here we are. In the same way, yeah, okay, there's the sort of, just keep doing the same idea to translate this. Okay, so edge to edge will then send everything, provided you get the orientation right. If you flip the orientation, then you're flipping this backwards, which is cool, but not quite what we want right now. You can imagine reversing a sequence is going to come up at some point. We'll look out for that. Is that the ones where after the initial number, there's a forwardsy backwardsy bit? Yeah, we've seen that pattern where there's like the continued fraction for roots of quadratics. Let's have a quick look in Wolfram Alpha. It's also in this book somewhere, but I want to mix things up a little bit by looking at a different thing. So I think you can just go continued fraction and I want something like square root 7, something like this. Well, that's not very exciting because it just says 1, 1, 1, 4. So let's try a different number like 17. Oh, well, that's just lots of 8s. So let's try 19. All right, okay, so here we are. That's an interesting one. I'm going to zoom a little bit. There we go. So continued fraction for root 19 starts with a 4 because root 19 is a bit more than 4. It's like 4.5. Well, when I say a half, I mean instead of 2 down there, I mean 3. 2 plus 1. And when I say 1 over 1 there at the end, I mean 1 over 1 and a third. Anyway, so we've got this 2, 1, 3, 1, 2. This kind of period, I think 8. So as you repeat that out, can I do fraction form? Ah, perfect. Look at this. Thank you, Wolfram Alpha. As you do this, it repeats 2, 1, 3, 1, 2, 8, 2, 1, 3, 1, 2, 8, 2, 1, 3, 1, 2, 8, which is nice because if you read it backwards, it says 2, 1, 3, 1, 2, 8, 2, 1, 3, 1, 2, 8. So that's what it looks like to be the kind of same forwards and backwards. 8, 2, 1, 3, 1, 2, 8, 2, 1, 3, 1, 2, 8, 2, 1, 3, 1, 2, 3 with 1s, with 2s, with 8s, with 2s, with 1s, with 3s, with 1s. 3 is kind of in the middle. It's putting it in this kind of repeated form with the bar over the top. The bar indicates repetition, like in repeated. Some people put bars over their repeated decimals. This looks like it's breaking symmetry because it's got this lovely symmetry bit and then an 8. But actually that does work if you have those on tiles or something and you put them next to each other, then it will look nice. Something weird, isn't it? You make that look better? Yeah, there's no good way to cut it. That's really weird. So if a sequence that's the same forwards and backwards, a palindrome or something, that's also repetitive palindrome, our notation for that's somehow not brilliantly perfect. Repetitive palindromes. Right, okay, well, I prefer this form, I think, for illustrating this point that it's the same forwards and backwards. Forget the 4. What number should I put there? 8? A beautiful fraction, please. Yes, great. Although that's disguised things a little bit, hasn't it, by cheating the first number out the front by just adding 4. Anyway, it's my fraction. I can add 4 if I want to. We get some control over this. I mean, we get control over everything, but this one's got a particularly nice format. Okay, same forwards and backwards, which I don't think I've ever understood even slightly, but it feels a lot like this sequence that we're considering. This one has not got this property at the moment because the sequence in the textbook at the moment is 2, 3, 1, 4, which this book uses these arrows and ones to give a little bit more of the illustration of what that means. But 2, 3, 1, 4 isn't the same sort of forwards and backwards. If I put 2, 3, 1, 4 and then another 2, 3, 1, 4, I don't get something that's the same backwards as it is forwards. Whereas the one we just saw, 8, was it 2, 1, 3, 1, 2, 8, 2, 1, 3, 1, 2, 8? It's sort of snaking backwards and forwards. So because it's snaking backwards and forwards, it has lots of 2s and 1s and not as many 3s and 8s. There's a lesson here about snaking backwards and forwards. Endless snake, I suppose, so I shouldn't be drawing the head of the snake, but hey. Okay, upstream, go. If you want to draw a snake at home, then go for it. Okay, so we're trying to understand that, by the way. In the continued fraction for the square root of 19, you get a repeating pattern, not maybe that's sensible, but you get one that's the same forwards and backwards. I may be developing a goal for today. Gosh, I hope it's not impossible, otherwise I'll be here forever. So sort of uniqueness of triangles, get the orientation right, and you'll map these triangles to each other. So you've got this big matrix that sends the whole thing translating down. And what would the flippy symmetry be? It would say that there's some point, some symmetry line where you can do the transformation that preserves that line. Maybe this one, maybe not, but swaps the other 2 points. So determinant -1 and preserving 1 and infinity. That's just minus signs, isn't it? Put minus signs on it, possibly. Is there a more interesting one? 1 over z preserves that line but flips orientation. Could just be 1 over z. Interesting. Okay, right. As a map. As a matrix for zeros and ones off diagonal, something like that. Preserve the line but not the... Okay, possibly that. I know, because I want to keep the line and the direction, maybe. Is that greedy? Sharply, triply transitive. Swap the other 2 points. Something else. Okay. Right, similar reason for the left as well. Tiers of translation. Good. Fractions labeling the vertices. Or the convergence. Yes. Take the limit. Ooh, this is good. When we apply the translation T, we're taking each convergent to a later convergence sequence. Okay, so the numbers along the top and bottom of this strip, as we're zigzagging in, we've got a matrix for what's going on now. So we can just apply that lots of times. Yes, here it is, look. Do the whole process lots of times. If you see that it's repeating, then do the whole thing lots of times. When I've given continued fractions to small children, not that small, when I've given continued fraction, I'm not that mean. When I've given continued fractions to children, I have got them to sort of work out stacks. I guess they can press them up. So you have this kind of, somebody gives you something awful like x is 3 plus 1 over 1 plus 1 over 4 plus 1 over 2 plus x. 1 over x, I guess. And then you can kind of multiply top and bottom to build this into a stack so that you have some fraction a bit like this with x's instead of z's for the limit. Yeah, converges to this for the fixed point. So you sort of multiply top and bottom. Like down here, you say, well, this is 2x plus 1 over x, and then flipped. So x over 2x plus 1, and you keep going. So you sort of zipper it up to put this all together. I don't know. I think we're going to find out in some sense. At the moment, I would say zipper it up and find the fixed point. So it's quite tough. I think it's going to turn out to be the square root of something nice. That's my guess. Like not 101, but maybe 101. Should we find out? I think Wolfram Alpha can do this the other way around as well. Forwards and backwards, right? 5, 6, 7, 8, 9, 8, 7, 6, 5, 4, 3, 2, 1. Repeating sort of bar or something. What do I want here? I tell it to repeat this. Oh no, it's not happy. No, it's not something random. Maybe if I click on a continued fraction, it'll give me some notation and I can copy their formatting. No, not this. I want to pass it. Plain text. Oh yeah, thank you. To the power of bar underscore. To the power of underscore. I'd never have guessed that. Thank you. Value of. So I want 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, 7, 6, 5, 4, 3, 2, 1. That's extremely fun to type. But maybe we want the only 1, 1, so that it repeats with just 1, 1. Maybe. So it does this. 2, 3, 4, 5, 6, 7, 8, 9, 5, 3, 2, 1. But it then repeats so that it does a 1 again. I think this. And now it's going to tell me it doesn't interpret that from continued fraction. No, it's interpreting my underscores wrong. In trouble here. Yep, okay, come on chat. We can do it. So I just need to copy, what's the Wolfram, I should probably look this up rather than guessing it. I'm having fun. Is this plain text? So copy this. No, because it's not done that. It doesn't speak its own language. I'm so annoyed. Why is there a power of underscore? Come on. One more time. One more time. I think we're stuck in a sort of loop, don't I? Periodic function, but it might be the same forever. What am I doing? Fraction form? No, not going to copy that. That's the code to generate it. Can I have these? Oh, I don't know what these mean though. Also, they're not the number I asked for. There's some big general functions. I don't know what they mean. Okay, so maybe I'll wrap that in curly braces for that bit. Or maybe that's just... something like this. Let's put the same one in. 21312. 8 or something. Just want 8. Close curly brace, close square brace. You want to interpret that for me? Oh, right, root 19. Okay, knows that's root 19. Good, we've got there. So, forget that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, 7, 6, 5, 4, 3, 2, and I don't want the 1. Ah, there you go. Good question. Good question, Maths222 in chat. Only took me a few minutes to get the computer to do that one. It's this irrational number that's about 0.69. There you go. It's the root of a quadratic, I suppose, is what we've learned. RFL, we tricked Wolfram Alpha into doing the thing that it's supposed to do. It is close to Lun2. But it's not Lun2 because it's algebraic. And I'm pretty sure Lun2 is not algebraic. Yeah, that was mad. Yeah, I've typed that correctly. I think that's what we wanted. Good, love it. It's got all these digits. I really thought that'd be something nice. I mean, I thought it'd be root 101, so wishful thinking. What is root 101? There's a rule for n+1, I think. That's jumping ahead of the textbook quite a lot, but if you want to play along at home or something, you might like to try spotting patterns in the continued fractions for things like just a couple of examples. These. So this bar again means repeated stuff. There's something going on here. So for n+1 is quite suspicious. You might also like to try looking for patterns in things like n-1 that I can't remember. Yeah, there's something going on there, isn't there? So you can maybe try and prove what's going on there. I think the textbook is going to get there. What's another square? That's a good square, that's a good square. So, oh yeah, that one looks quite nice. Loads of 28s, good. And then n² -1. Yeah, so I'm just taking some square numbers, adding and subtracting 1, pointing at a pattern and saying, look, can you work out what's going on here? Why is it doing that? I suppose I mean, can you take something like this in a general format, zipper it up, evaluate it, and show that it's something like this? That's the easy way around, rather than starting from square root of n² +1, n² -1, or whatever, and trying to calculate its continued fraction. Easier, I think, to start with the continued fraction and then zipper it up and show that it's equal to the number. Cool, right. Right, fixed points of transformations, and they're going to zipper up to be. The big transformation for this repeating pattern is always a Mobius map, so it's one of these. So it's going to be root of a quadratic because you're going to solve 4z + 19 over 9z + 43, and this example equals z. That's a polynomial of degree at most 2. Have fun. Yep, this simplifies this quadratic. Here's the roots. Good. Yep, okay. Lovely. The other root has an interpretation in terms of the diagram as well. Limits of the numbers labelling the vertices of the zigzag path moving off to the left rather than the right. That's the other root of the quadratic is over on the left. Brilliant. The numbers written backwards. That's really weird. Is The limit of the numbers labelling the vertices of the zigzag path moving off to the left and the right. Same sort of argument as above. Right, so moving to the left is the map T inverse Z. It's that's fine. Actually, it's just a sort of matrix multiplication, I suppose. So same sort of idea as Z equals TZ. So it's not surprising that it would be the same quadratic as the other solution. Yeah, the other fixed points at the other end. That's mad. So this kind of rainbow of semicircles stacked together, joining together the two roots of a quadratic. That's really silly. Okay, love it. That's really daft. That's kind of brilliant though. I really want to illustrate this. Can we That's so good. They just join up. It joins up the roots of the quadratic, left and right. So how's this quadratic thing going to work then? If it's just the root of, what's the symmetry thing? Forwards and backwards. What's that going to mean? Well, I was going to say the T inverse is the same thing as T, so it's the same number on both sides. That's a bit weird, isn't it? If this thing looking left is the same, then I think you're going towards the same number, and now I'm confused. So this is going to come back round again to the same point, maybe? No, because your quadratic is going to have two roots. So which ones are we going to talk about when we have the symmetry? Okay. Right, odd lengths. I called it. I knew odd and even lengths was going to be relevant. Well, I wasn't sure. Okay. And there's a glide where you also do a reflection across the horizontal axis. So this sort of stuff ends up 1, 2, 3 over here, and then down here, and then up here. Transformation is typical glide reflection. Orientation reversing is determined as -1. Why did we do that? Why did we send that arrow to there? Oh, after the threes. Yeah, we could do this one, or we could do the opposite, right? We could send it. We could also flip, but then we'd be going to the other side. Each successive triangle. Yeah, okay, check that it's doing the right things to triangles, fair enough. I've come around to this way of arguing. It seems convincing. Now I've checked some basics. Just watch where the triangles go and you'll be fine. I've checked that that's well defined or something. Realised by a linear fractional transformation, good. Proceeding for example, the value of the continued fraction determined by solving that, where you get the roots for quadratic. Yep. Continued fractions that are only eventually periodic, interesting. Does that get me out of thinking about why only eventually periodic? Yeah, this gets me out of thinking that the roots are the same thing when you go left and right. That's only the case of ones that are periodic both ways, with like 4 plus root 19, where I made the 8 correct as well. Possibly. Maybe that's where this is going. Where the root 19 itself had that weird 4 at the front. Maybe that's different. For example, consider something like this. Then you have some stuff at the front, and then it gets into this nice pattern. We have to discard that stuff and extend the remaining periodic part in both directions. Ooh. Carried to itself by the glide reflection, taking. So we've kept this bit. We've kept this bit in, but got rid of these 1/2 plus 1/2 stuff at the front. So eventually periodic. Right, so then that one translates nicely with this map. So, okay, what's this then? What's going on here? This is going to be some sort of just standard matrix change of basis sort of thing. Compute T as a composition of two transformations realising the two-step combination. T, what was T supposed to be? Glide reflection, taking this to that. Oh, but do it 2 steps. Yeah, okay. We've seen this trick before. To work out how to get from some line to some other line, consider taking it back to 0, back to the kind of basic line, and then out to where you want to go. This is the British Rail solution to problem solving. The British Rail network works by having anything you can think of connected to London by a train service. So then if you want to get from any points to any other point, that's possible. Proof, first get the train on its way back to London, and then get a train that goes out from London to the place where you're trying to get to. So the existence of this kind of inverse train is also important, the one that goes back to London. So from the planning point of view, if you plan trains that go out from London to all places, then it will be technically true that you can get from any place to any other place. So there's kind of inverse train here to get back and then go out to where you actually wanted to be. This is a standard complaint about British Rail that is so old that you call it British Rail even though it's not called that anymore. It's an ancient complaint. Sure, yeah. Although, is it a vector space if I can't? There's a sort of star graph, is the graph theory word for this. The other thing that people say is the British Rail metric, which is where you define the distance by distance to London plus distance from London out on the other side. So, is it a vector space? I don't know, what's addition? I don't know. Yeah, no, I'm not sure, because like, Britain is not infinite, so so I've got cold feet on the vector space. Maybe it should be. Hooray! Right, okay, good. I'm having fun. Almost tea time. Accidentally extended the British Empire infinitely large. No! Somebody stop them. Right, okay, we've got this matrix transformation, which is mapping this line to that line. We've got some horrible looking calculation for actually working out how to get there. We're going to do that lots of times. This transformation to -1, so it is the glide reflection that we want to find. Now we solve that to find the fixed point with this, but don't forget we were going to do some stuff at the front. This feels silly, but not too silly. We want the smaller one because along the top edge of the periodic strip the numbers decrease. So have this trick for working out which one is at which end of this infinite strip. Interesting. Thus we have some stuff adding on the numbers at the front. Okay. Do we? That's surprising. That's the fixed point of this map. With the halves on the front as well. With the halves on the front. Oh, thank you for the follow, Honeycat. Good to have you with us for Chill Maths. We are calculating with continued fractions and complaining about trains. That's how we do things around here. I missed a live stream last week, partly because I was on a train. Although, in fairness, the train would have had to be really extremely fast for me to get back in time. Right. Notice that root 37 is in both. Nice. Hello. Good. Yes. Welcome to chat as well. Good. The root 37 appears in both of these. I'm not convinced that we have got with these halves on the front as well. I kind of missed that happening. I think I was complaining about trains at the point where those numbers came in. Adds to an inverse, then adds to an inverse again. And each of these operations of adding an integer takes its place within the set. Galois theory flashbacks. Q adjoined with root 37. All numbers of this format. They're good numbers, aren't they? Any rational number you like, plus any rational multiple of root 37. That's a good field, isn't it? Is it a field? Yes, James, it's a field. Is it a field? How are you going to divide? I'll get to that. It's a vector space at least. Yeah, no, you can rationalise the denominator. That's how you divide. Come on. Yeah, that's just something people say. You can sort of keep adding things in. Good. Yeah, adding one of the things you like. I'm trying to remember the formal way of doing that. Rather than just saying, look, I'm going to throw all of the square roots of prime numbers in. What are you going to do about it? Maybe that's good enough. What are you going to do? I've thought of some more primes. Yeah, it is a field. It took me ages to work out how to divide by 1 plus root 37 until I remembered that 1 over 1 plus root 37. How do you write that in this format? How do you write that as in the format a plus b root 37? And then I remembered about rationalise the denominator. You write it like this. And that's now in the format of rational multiples of root 37s and rationals. Good rationalising the denominator. What fun. Do you ever get 0? No, of course not. Why would you get 0? Only if 37 is rational. Only if root 37 is rational do you get 0 through this process. Proof for the reader. Proof that this never goes wrong. Look, I'm dividing by, in this case, minus 36. Proof that I never get 0 when I rationalise the denominator of one of these things with numbers here and here. Right, yes. Good. Okay, wow, suddenly having loads of fun and loads of Galois theory flashback. For people new to the stream, we started this experiment in 23 by doing 5 days, 9 to 5 Galois theory. I had a week off and I just did Galois theory on Twitch for an entire week. It was certainly a thing. It was not good TV and it was also not a great way of learning Galois theory. Right, 2025 quest, here we go again. Yes, let's have another go. 3 minutes until 3. Here we go. It's been a year and a bit, year and a half on Twitch. Here we are. Yeah. Woo. We've done a lot. We've done natural number game. We've done biscuit balancer. We've done some number theory, and there's some more number theory, and there's some more number theory. And maybe the third time it'll actually stick. Maybe I'll actually learn something. We very briefly did some integration, but not very much. We're on a learning journey. There's no time limit. I've realised that this is what I needed. There's no time limit for me to learn any of this. There's no exam. There's no you have to graduate in 3 years' time or something. There's no like you've got to publish a paper. There's no test. It doesn't matter if I take 10 years to learn this. It doesn't matter if I don't learn this in the next 10 years. Right, but here we are again looking at Q adjoin root 37. It's like an old friend at this point. Here we are. Right. Okay. More generally, this argument shows that any eventually periodic continued fraction whose periodic part is this, where, what do I think? That stuff represents some number in here, and you could do some fraction stuff to it as well, where I will do some rationalising the denominator to simplify this up to get something in this set. It has as its value some number in there. Good. Not all irrational numbers in here have eventually periodic continued fractions with periodic part this. Yeah, okay, don't always end up with a root 37. Or no, sorry, you don't always end up with that sort of continued fraction. Different periodic part. Okay. 37 is 1 plus 36, so it's one of the ones that I asked you to think about 10 minutes ago. How does your argument for inverting generalise to 1 over 1 plus a root 37? I suppose I'm going to multiply someone by 1 minus a root 37 and hope for the best. And I'm going to get 1 minus 37 a squared down here, difference of 2 squares. So in chat, 1 over this. So I multiply by this, and I get, well, downstairs the product of these two things is the difference of 2 squares, 1 minus a squared, and these make 37. So I should worry a little bit. Well, what if 1 minus 37a squared is equal to 0? That would be pretty embarrassing because I'm really not supposed to divide by 0. But luckily, it's definitely not 0, is it? If a is a whole number. If a is a rational number, then still think I'm fine because 1 over 37 is not rational. I think I can put some b in here as well, right? So I have a, I could probably put number b here, a b here, a b squared here. And then I'd like panic. Let's put some b's in. They're in slightly weird places. What if, and then what if b squared minus 37a squared is equal to 0? Uh-oh, that would be bad if I were dividing by 0. But that rearranges to say that then b over a is root 37. And root 37 is irrational. But root 37 is not in Q. So then we're calm. We are happy that this never happens and we've managed to divide by any number in Q adjoin root 37. It's important when you do this not to chuck in a number that you've already got, is the take home from that, if you want this to work. Yes, I could, that was much cleverer, Honeycat, thank you. I could have just divided top and bottom by B first. Yes, I'd already said what if A is rational, and that's enough. Yes, there you go. Find the degree of the extension, root 2 plus root 3 plus root 5 over Q, and that one has dimension. Wait, hang on, I forget if you're supposed to have 1 or not. Oh no, you've added all of them, so you've only adjoined one number in there. Oh, I can't remember how to do this. Right, we're going to take a tea break, which is a chance to go and make a cup of tea. Maths 22222 is set you some challenge over a tea break. It might be 8 or something. Feels like how many powers of that number do you need until you can find some combination? What's is that called the algebraic degree? Oh, it's all slipped away from me a little bit. Algebraic degree? Algebraic degree of a number? Is it? That's what it's called. The algebraic number is the degree of the polynomial that number as a root. Ah, I remembered a word. Algebraic degree of the number. Possibly 8. There you go. Hello, Mimicry Rex. Good to see you. I'm about to do an ad break. Not because you got here, but because it's 3 o'clock and I want to get more tea. Right, back in 2 or 3 minutes, depending on kettle speed. See you then. If you want to make a cup of tea, go for it. If you want to watch some adverts, got you sorted. I didn't know you could do that. Right, that's double tea. I didn't wasn't aware. Right, I guess I've got to make 2 cups of tea. Right, see you in a minute. Ad break. You are not missing anything because it's just going to say back soon. I'm back. Bye, Herb, if you still hear Herb's left to do work. Or Mean Machine Rex says that it redeemed custard cream. I didn't know I had a setting that could allow 2 people to say that I have to drink a cup of tea, but that's good to know. Got to change that one. It's going to get out of hand. Hello, Phobos Stream. Good to see you as well. Right, what are we doing? We're learning. What are we learning? Who knows? If you joined us for the first time, I find the outbreaks a good way to refresh and think about what on earth we're doing here. I often come back with a sense of sort of, what is this? Right, yeah. I'm pretty sure I set a cooldown on it that we couldn't get into this kind of like looping T situation, but here we are. Right, okay. We've got repeating continued fractions. They're periodic. And we've got a kind of guest appearance of field extensions from Galois theory, sort of. So that's exciting. We've been warned in this paragraph that some things in this set of numbers of this format might not have this particular sort of continued fraction that ends like this. Indeed, this number itself does not do that. But all of the ones that do have that format because you evaluate that. If it's eventually like this, if your continued fraction, which, reminder, they look like this, stacked fractions. If it's eventually periodic, stupid example of one that's eventually periodic, but not, all the way down is this, where that first number is not part of the periodic pattern, but eventually gets a periodic pattern. The idea is that you say, I see what's going on here. You chop at some point, evaluate the rest using fixed point methods, sort of, to say, this is a repeating pattern. Let's call it X and find out what that number is. You hope that it converges, but we've got some convincing chapters 1 and 2 of this book convince us maybe that this converges. And then the other steps, once you've worked out this long tail, the other steps are just rational functions. So you end up staying inside here. We've checked that you can divide by numbers in there and stay in there, that it's a field. Good. Good. Everything's under control. For the periodic part of the continued function, works in general for any irrational number set whose continued fraction is eventually periodic. Good, love it, brilliant. Just do the thing in general with numbers in for what your transformation is to the fixed point. This is the thing I just said out loud. Love it. Satisfies this fixed point sort of the operation. Quadratic, solve the quadratic, get 2 roots, think really hard about which one you want. Ooh, the coefficient must be non-zero. Here we go. Suppose on the contrary that you got 0. They're going to insist that it's a quadratic. Determinant with force A to be plus or minus 1. We know what sort of matrix we're working with. And then for the first column of the matrix, we'd have this. We'd see that T would take the vertex 1, 0 to itself. Okay. Yeah, this doesn't do that. Okay, it's got to actually go somewhere. Nice. Oh yeah, there's a capital K that I've only seen in the context. Sorry, I missed your chat question. I've only seen the capital K in the context of I'm looking up a continued fraction on Wolfram Alpha, and it will show me this notation. I've never seen it anywhere else. I could probably find out what it means by clicking on it, but scary. Also, I think all the examples. Is this mad? I've typed in a specific question about a specific continued fraction, and then it's showing me just some examples. These are unrelated to the question I asked, so I don't really know what's going on there. It's kind of like it's not an advert, it's not promoted content, but it is a bit like you've done a search for a continued fraction maybe you're interested in. Big K notation. So I've never been that interested because I only see it in Wolfram Alpha, and I see it for numbers I did not ask about. So lovely, right? Oh, look, log 2. That's the number that we were thinking about a moment ago. It's got some K notation thing going on. What is this? So maybe I just click here. Brilliant, love it. Okay, if you want to know about continued fraction K, you can learn about continued fraction K at this URL. Have fun. It's a Gauss thing. Oh no! I've disrespected Gauss notation on stream. No way I recover from this. Right, oops. Compound in German. Oh no. Oh, actual disaster. Right. Okay. So it's going to be an actual quadratic. We've been told this map that you're finding fixed points of actual quadratic. None of this like just a linear map because it's just the identity. Woo! None of that. 2 solutions. Quadratic equation. Okay, good. This bit's consistent with T of Z just being the identity for all Z. Find the fixed points, all of them are fixed points. It's the identity map. But this line of maths is to try and rule out that possibility by not sending this line to itself, which feels like ruling out fun, but never mind. I guess we want to talk about irrational numbers, not the union of irrational numbers plus weird fun time. Anyway, where are we going? Let's just go there and find out. The other vertices line, what? Oh yeah, it doesn't do that. Right, great, okay. Apply the quadratic formula to deduce that it's this format. Good. Real numbers are defined by that. N cannot be negative. We know we're going somewhere with this continued fraction business. Cannot be a square since it's irrational because it has an infinite continued fraction. 1/2 of Lagrange's theorem. Here we are. A real number whose continued fraction is periodic or eventually periodic is a quadratic irrational. Yeah, zip it up. Get probably a quadratic, solve the quadratic. Seems good. The converse statement is in the next chapter and the chapter after that. So 2 more chapters to get the converse of this fact, which says that for any quadratic irrational you can find some repeating periodic thing, which you would need to understand, I imagine, why root 37 up here does this sort, and some of the numbers in here do this sort of continued fraction. It's not going to be as easy as just saying 37 means you're in this sort of group. Right, what is going on in here? We're going to look at what sort of quadratic you get. Oh, there's a table. Here we go. Fixed point this is, and then here it is in terms of what your numbers in T were. They appear here. This has roots to this. So really following it through for a general T, AZ plus B over CZ plus D. Maybe it's oh, there it is. If you let it be plus or minus 1 for the discriminant, or the determinant of the matrix, then we get this, and the roots can be rewritten like this. Yeah, you've got some minus AD going on in there, haven't you? Okay, the discriminant is this, determines the nature of the roots. If delta is positive, there are 2 real roots. Yes. If delta equals 0, the 2 roots coalesce to a single root. Good word. The single rational number, so not in any of these cases, because a rational number, a rational number wouldn't have an infinite continued fraction, so that doesn't happen. And if delta is negative, I don't think that happens either, because, well, I don't see why it can't actually. It's like a trace squared minus. Yes, here we are. Trace squared. I'm 1 sentence ahead. Trace squared minus 4 times that. So matrix satisfies the same characteristic polynomial, and then mumble eigenvalues. Mumble eigenvalues. We're always in the positive case, maybe. Sorry, stupid question. No, you just make A really large and D also really large. No, that makes this really big as well. Don't mind me. It's not symmetric, but what am I doing? What am I doing? Right, you just this. Sum of the eigenvalues minus the 4 times the product of the eigenvalues. Is AD minus BC the product of the eigenvalues? Yes, it's the discriminant of the two matrix. I think this seems always... never mind. Okay. I also think it's always positive because I think you're always going to get solutions for these because they're at the ends of the... What else? It's not going to converge on a complex number, is it? What? Okay, trace like this, a matrix and its negative determine the same transformation in here. Okay. Usually assume the sign of the matrix is shown to make the trace non-negative. Fine, okay. Here's a table. Wow, okay, good. What on earth is this? Identity transformation of trace 2 fits into this scheme. Pivoting transformation. Okay, what are we talking about here? We've got specific matrices in mind for these. This is something like, I think, this one. It's for 180 degree rotation. But they're saying determinant plus 1. Oh, I don't know what's going on. The trace to 0, which I agree with, but why the minus sign on the determinant? Oh yeah, I've done a reflection, haven't I? That's a reflection. Yeah, okay. So we have those pivots, I've forgotten what they were. Is it keeping a point fixed and moving everything else relative to it? Something like that, wasn't it? That's determinant plus 1 and it's not the others. It's not fixing a triangle. It's fixing a point rather than fixing a triangle or an edge. Yeah, so this is fixing an edge. This 120 degree rotation is fixing a triangle. The pivot is fixing a point, I think. The translation fixes nothing. So I don't know where to put it. In these translations, live reflections fix nothing, and the reflection fixes an edge, but in a different way. So an edge, you get 2 sorts of transformation. If you fix a triangle, you get lots of things. I guess you get 2 sorts of rotation. And if you fix a point, you can do loads of stuff if you fix a point, right? Mean Machine Rex asks, how many vertices does a tesseract have? And I think the answer is 16. Because you've got 8 for the cube here, 8 for the cube tomorrow, and you join all the dots. Cube's got 8. Yeah, it's just powers of 2. It's 2 to the number of dimensions, right? Yeah, 2 to the power of number of dimensions. Square, cube, hypercube. Good-o. Right. Right, I think we're going to prove my trace facts now, probably. Oh no, 4 of the 6 rows on the table. No, here we go. Yeah, I wanted to know that thing was always positive. There were several cases up there somewhere. Several cases up there. And I think only one of them is real. But we'll get there, perhaps. I think there's a relationship between the trace and determinant for a matrix with real eigenvalues. Why do I think this has got real eigenvalues? Why do I think this has got real eigenvalues? Okay. Oh, I erased it. Must mean. Why do I think this has got real eigenvalues? Yeah, maybe I don't think this has got real eigenvalues. In which case, the square of the sum of the eigenvalues might not be positive. Right. Okay. Good. Well, goodish. Now I think it might be converging on complex numbers again, which doesn't make any sense. Trace does this. Yeah, you can do a boring transform calculation for 2x2 matrices. The consequence is that trace is preserved under this. Fine. Okay. What are we doing? Why What are we trying to achieve? I'm skim reading this now. Okay. Okay. Oh, right, so we're going to work out whether these things are positive or not in the different cases. Every symmetry is one of the 6 types. Okay, that's quite good. Translations have 2 distinct fixed points. Oh, right, thinking about the fixed points like I was down the left. Taking traces of non-negative requires this. Discriminant of the fixed point equation. That's a bit much, isn't it? Is this? Is that have we got that phrase from the previous page or something? Is this a new concept? Discriminant of the fixed point equation. Yeah, I think that's what we're calling this. The fixed point equation is a quadratic, so the discriminant of that is the discriminant of the quadratic, I suppose. Good. Always positive, however. Can't be 0, 4, points will be rational. So the glide. Okay. Don't know exactly what the transformation is. Simple matrices like this. Okay. It seems reasonable. These are the, well, that one's the medium rule again, I think. We've seen this in various disguises. Adding on. What does it do? I always do this little calculation and it always confuses me, so maybe I shouldn't do it. Yeah, I'm confused now. Because this doesn't look like I've added on n of anything onto my original fraction. It's now upside down, so I'm confused. And I think the answer last time was no, you're supposed to put it on the left or something. I don't really understand why, but if I put it on the left, is that nicer? Not really, I mean, what are you doing? Transpose here. If you put it on the left, then this is just silly, because now I get exactly the same thing, don't I? I'm going to get exactly the same thing. What am I doing? What am I doing? I don't know what I'm doing. I always confuse myself, and I managed to say I was confusing myself while I was confusing myself there. It's a new light. Okay, whatever. Look, we had these matrices before. I can go and look them up if I want to. They determine continued fractions. They're good. From this, it follows one can determine the type of. This proposition will not be needed later in the book. Proof is not very difficult. So small digression. I think I maybe skip this on first reading. Let's see. Oh yeah, okay. So it's going to think about the points. That's quite nice. How long is this? Quite long. That's good news. Okay, we're going to skim this proof. We're going to read it together. So forget the identity for a moment. If t takes a triangle to itself, you've got to rotate or reflect. Yeah, so I paused when I was thinking about fixing a triangle because there's loads of symmetries of triangles, like 6. Oh, not the identity, 5. Hence the whole fairy diagram. Yeah, because you patching triangles onto your triangle. Similarly, if t takes an edge to itself, then t must be rotation or reflection. We thought of those. I don't like this proof. It's just telling me that here's what might be going on. Let's go to the if no. Yeah, okay, the if case here is going to have to do some convincing to make sure we haven't missed anything. Vertex itself must be a pivoting transformation. That is what they were. If t takes no triangle edge or vertex to itself, we will show that it takes some infinite strip to itself. Cool. By translation or a glide reflection. You're going to move your triangle somewhere. Where are you going to put it? Maybe you will say you want to move your edge somewhere. Where are you going to put it? If there's where are you going to put it? I will then follow to see where you put t squared. I'll do the transformation again, and they will probably be connected. Or if you can walk from one to the next, then keep going. And you probably can walk from one to the next because these triangles form a kind of connected region. So find the image of, take the image of the triangle. Where's it gone? Oh, it's over there now. Walk along any, I don't really mind which one, any path to that triangle, and then do it again. And now you've got an infinite strip. Same t? Same t. So do I think there's a unique way to walk to the other triangle? Or is this a bit mad? Well, let's read it. It's on screen, isn't it? So let's just read it. Infinite strips stuff. Motivation. Observe first if T is in fact a translation. Triangle the strip label sequentially. Oh yeah, we did some labeling triangles. Good. Interior point of Ti and interior point of Ti plus 1 causes n edges. To find the distance between two triangles in the diagram to be the minimum number of edges that must be crossed. We're going to take the shortest route. No messing around. Yeah, graph theory, mumble. Connect two triangles if they share an edge. Think about the graph distance between these points. Use an algorithm if you want to. Interior point of the other triangle. Distance is like this. Oh, in our infinite strip, yes. For any triangle T that's not in the strip, distance is greater than n. Since it's this, where K is the distance from T to the closest triangle in the strip. That doesn't seem obvious, that you can't take a shorter route than going via the strip and then... What? 2K? For any triangle T that is not in the strip, the distance from T to the image of T is greater than, since it is out of nowhere, n plus 2k, where k is the distance from T to the closest triangle in the strip. Do we think this is unique or something? Was that you could walk to the strip, walk along the strip, and then walk out the other side? Why are we saying that's the shortest distance? And then more than that, we're saying therefore. So we need to prove that that's the shortest distance without using the fact that that is the shortest. It's longer than the other. Without assuming that going along the strip is the shortest distance, please demonstrate that the shortest way to get from A to B is along the strip. What? Is there only one way to get from a triangle to another triangle? No doubling back? Maybe that's true. Maybe that's true. The triangle points to the triangle all the way to the sides. So maybe there's only one way to do this. If you get your directions wrong, then you can't come back because you'd have to cross infinitely many triangles or something. Let's have a look at the fairy diagram. We're on page 91 on the slider thing. Let's see if we can find a picture of a fairy diagram. There's not going to be one around here. There's going to be a picture of a fairy diagram. I mean, there's one on the front cover. Let's have a look on the front cover. So the question is about walking around between triangles. So if I want to get from A to triangle down here B, I could walk like this. But then the observation is there's no real other way of doing it, which is... Or if I want to get from... No, there's loads of ways of doing this, right? Because I can go... I had a double back. We had a bit on this earlier on, didn't we? So you'd have to double back. So if I'm not allowed to double back, then I have to keep going deeper into the diagram without kind of... If I'm trying to get to B, then I'm taking this kind of wrong turning. And now, unless I'm allowed to double back, I have to keep going further in. Because... So actually the kind of path from A to B kind of is unique if you remove silly doubling back stuff. That's not obvious. That's a kind of cool topology kind of thing, right? I don't know what to do with that. Definitely don't know how to prove that. I mean, not unique, like you could go somewhere else inside here and cross the same edges and also get to B. But unique in terms of the sequence of triangles that you follow if you're not doubling back. This one. And then if I go over there, maybe I come back again. Or maybe I'm now stuck. Why do you need uniqueness of part? Well, the argument on page 91, something I suspect is true. maybe it's not obvious enough that I can use this fact in my understanding, but I don't want to assume something powerful that I can't really prove. But there's something going on here where the underlined bits over here, they're talking about some kind of magical strip of triangles. They've got some plan where things move, and moving along that strip, they move by n. And it sort of says, as if this is obvious, maybe? I should read this bit again, I think. Any triangle T that's not in the strip, so any other ones, the distance to get to T of T, which this T could be anything, and then we're looking at the image of this, is apparently n plus 2k. They say that you should go, or an option for how you can go, the best way to get from T to image is to go, and I don't really know if this makes sense, to go from to the strip, along the strip, and then out the other side. So sort of work out how to get onto the strip, which we understand, go n steps along and then out the other side. It is a binary tree sort of thing, so yeah, that's probably enough, isn't it, for the topology kind of. For the topology crew, you've got a pretty strong understanding of where stuff is. So without messing around, I think the argument here might just be, without sort of messing around where you go into a region and then immediately back out again, the best you can do is sort of almost unique. You go to this infinite strip, which is going along in a very particular direction. It's moving everything in that direction. That's mad. Where's it ended up? K plus n plus k. That's not really how the triangle inequality works. You can't just say, I found some route that takes k plus n plus k steps. Can't be better than that, because once you've found a route that doesn't do any messing around, anything else would involve messing around. That's sort of mad. It's like London, right? It's like the London argument. There's only really one. If you explore the rail network the other way, then where are you going? Only there's something going on in London, so you gotta go to London, do the London thing, and then come back again. Right, okay, I sort of believe this now, I think. I don't really know why I believe it. This textbook, I like it, but this textbook does sometimes have a proof where I don't really understand the detail of why it has to be like this. We really rely on, at one point, on the idea that an edge has got two sides, or that, I mean, it definitely does, but what are we actually doing in some of these proofs? Yeah, it's probably just this, isn't it? Math tutor is pretty convinced about this binary tree stuff. So it's like binary tree. Here we go then. It's binary tree, where your plan is to send. You've got a function that is going to send this point over here, and then underneath, everything's going to follow underneath. So the images of what am I doing? Where's the top stuff going to go? Where's the top stuff going to go? What's my big plan here? The binary tree's got a weird point at the top with degree 2. That seems quite bad for me to do a fixed point transformation on this. Do any sort of transformation. Nothing pointless to themselves. What's this binary tree thing like? Oh yeah, so my structure is actually not quite a binary tree, but stuck to another binary tree. Right, I have the other half of the circle. Oh, this is silly, isn't it? I have this structure. I have two binary trees stuck together, one for the negative numbers, one for the positive numbers. And my plan is to imagine a map T that sends... Oh, goodness me. To somehow pick everything up, deform it, and put it back down so that circles go to circles. I don't think I've drawn the right picture to help you imagine that, but everything's got degree 3, so maybe it just works out. No, surely not. Really? Yeah, maybe everything just works out. It's not obvious. With this model of how these things transform, it's not obvious why you can't just flip the lower half and not the upper half. There's some sort of like stronger stuff going on than just connections between triangles. Flipping one triangle over also flips the neighbouring triangles over, which flips which one's which. So there's some sort of global property going on about whether your areas are being flipped upside down or not. That is the right picture, isn't it? If I go back to the front cover, still on page 91, the front cover has, we're mostly talking about a series of triangles that are arranged in a kind of double binary tree. Let's get rid of the root for now. We've got one up here, one down here. There's some distortion from the one I just showed you, but we've got this kind of binary tree. Oh, yeah, so I've missed a little bit there. And across the middle, these things are connected down the middle. So we've got this. Ooh, yeah. Yeah, I should probably start writing numbers down, shouldn't I? Write down lots of numbers. For an encoding of which triangles we're talking about, and then reinterpret all of the maps together. What's going on there? But this makes it more clear, I think. Once you've gone down here, the kind of shortest distance is basically uniquely defined with it, unless you do any messing around. So if you actually want to find a route to one point, finding any sensible route that doesn't do any backtracking. That's why we say shortest route to the periodic bit, to the infinite strip or whatever I was calling it. No, we're still only a quarter of the way into this book. Am I going to spend a whole year doing this book? Am I going to spend a year live streaming this book? It's more likely than you think. I can't spend a year live streaming one book. That's. Oh well, here we are. I'm learning about continued fractions. I think we're getting to the good bit. Also, I think this book has number theory in it afterwards. So I think we could learn about which primes are the sum of two squares or something like that. Yeah, then we've got 1,000 pages of Evan Chen's napkin. After this, are we doing the hard one? Yeah. This author has several books. This is the easy one. Right, okay. Yeah, this one was recommended to me for being a fun way to think about continued fractions. I'm aware of other ways of doing this, and parts of reading this are provoking me into thinking about, do I really understand the Euclidean algorithm? What are we really doing here? I'm not really sure how much I care about continued fractions overall. They're nice. Really not fun, okay. Right? I like the visual stuff in this one. A bit. Yeah, no, I do like it. Some of the proofs are a bit annoying because you have to think about if they really understand the connections of regions or whatever. And sometimes we translate proofs into little bits of maths, but I think it's going okay. Right, good. 20 to 4. Right, if it doesn't know symmetry, follow stuff to see where it goes. This is surely it. We mumbled something like this out loud 10 minutes ago. A minimum distance that any triangle's moved, that sounds great. Very clever, like it. Yeah, okay. What does minimum distance mean? You've got some triangles. Good. Yeah. Okay. And then keep going to iterate and find out where things are going. In fact, the T inverse also takes no triangle if T itself does not. Yeah, fine. Okay, so this proof is just going to say follow what's going on, keep iterating. It does some weird transformation. I'm trying to imagine it sort of turning and spiraling things in. Might be fun. Can we imagine it? Can we visualize it happening slowly? Seems like a fun Desmos for wrapping this up. Repeats argument. Let's finish skimming this proof. Backwards, infinite strip, fine. T inverse also does this stuff, so it's fine. And the triangles join together, so it's all going to be fine. Yeah, minimum distance means it's periodic with that thing. Yeah, okay. 5 intertwined sequences of polynomials. Okay. Yeah, okay. Right. Yeah. Right, tiny bit of Desmos. What do I want to do here? So I've been thinking about this as a map of the upper half plane. So I think I'd like to visualize one of these as a map of the upper half plane. That's the numbers up here. I'd like something like, so I've got some map. Are we going to use complex numbers? I think we might. AZ plus B over CZ plus D. Enable complex mode. Best thing that Desmos has ever done. But include a new complex mode. So then you can put in your favourite numbers. Let's see if I can remember some numbers. What was it? 19 times 9 and 14 times 40. 4 times 43. 19 times 9. Let's just check. Minus 1. So I think I should flip these two around. So 43, 19, 9, 4. Right. So we've got one of these AZ plus B over CZ plus D. I would quite like to understand this map. For example, I'd like to know, well, what does it do to sort of innocent looking points like 1, 1? I guess 1 plus I is how I write that now. Complex numbers. Oh, it sends it over there to basically 0. Imaginary part. What's going on there? I didn't expect that at all. Am I happy with this? I don't know what's going on. Oh, it's really cross with me now. Why? I have to find A, the number in multiple places. That's why it's cross with me. What on earth? Am I going mad? Why is this constantly valued at 2.26? No matter what numbers I put in. What? What have I done? These are just numbers. AZ plus B over CZ plus D. What? Why is this the constant function? Why is it wheeling around a tiny bit, but not lots? What am I doing? 2.25. Amazing stuff, love it. This is mapping everything. Oh, enormous numbers. Oh, it does map everything really close to 2.26 because that's something like the fixed point. It's a lot of things. This was a big map that's sending everything really close towards. Good observation. This is sending everything really close towards, well, the thing that's infinite continued fraction is going to converge on, which is somewhere around there, I guess. Okay. This one feels too powerful for me to visualize, or something. Maybe not. Maybe if I had some, so if Q was some sequence of points, let's try and find some sort of semicircle and see what happens. I'm going to give it a random semicircle, but then I reserve the right to change this to an actually good semicircle in a second. So I want pi from 0 to 1. A little cheeky semicircle. Wait, Desmos is good at semicircles. It's good at equations for semicircles. I want a parameterized thing like this, right? So I can talk about the image of this semicircle. And it's going in towards, you have to zoom in a lot, but it's going in towards a tiny semicircle. Oh, and it's redistributed all my points. So this is going to be a pain for drawing semicircles, isn't it? Because if I just join the dots, it's going to really get me. Okay, but we can talk about images of semicircles onto this map. Good, Maths2 is way ahead of me and has already drawn this. Oh, look, it's all of the things from before. All of the semicircles in the fairy diagram. Well, some of them. And then you're going to map them. Whee! Yeah, and mostly they're just shrinking in towards that because we've got a huge amount of scale factor. I think I want a smaller one. Smaller example. 0, 1, 1, 2. That's determinant -1. So that's all right though. 0, 1, 1, 2. Determinant -1. Oh yeah, I don't have -1. What's that doing? Yeah, okay, fine. 1, 2, 0, 1. That's determinant 1. And then I want to think about how this is. Oh, is this just a translation? This is just a translation, isn't it? I've set the C to 0. This is just a translation. That's too easy. Okay, better than that. Cool, it's just a translation. Right, hang on. Okay, so let's do better than that. Let's put larger numbers like. Yeah, okay, fine. I'll use 0, 1, 1, 2. It's got determinant -1 though, which is why I wanted to flip them. But I suppose if I flip them, then yeah, this is just a translation. Then the -1 is inverting or something. Oh, is that just because? Why is it going upside down? Why is my image going upside down? Oh, because I was mapping to the negative numbers, which feels silly. So maybe I should just make this negative? Should make B and D negative or something mad? 0, 1, 1, 2, but wait, actually -1? No, it's got a +1. But this looks maybe non-trivial. Like different semicircles are mapping to different size semicircles. Different radius semicircles. Okay, so maybe they're mapping something interesting. And there's some sort of fixed point over there. So maybe... This is daft, isn't it? I kind of want to visualize the transformation that takes me from the red one to the green one. But I don't just want to translate and scale, I want to try to move it through. What do I want? I want to move it through. If it's secretly just a translation, then you should animate it in translation space, but deform it before and afterwards. That's made no sense, I'm so sorry. But yeah, so this should be like the... I should do this, but then also have the translation as the kind of animation parameter, which should be an integer, but we could make it real for the slider to say you're going to translate, because that will sort of disguise what the translation looks like. So I've got, in some sense, sliding for translations, sliding naturally is fine. For the other ones, I'd like it to try and sort of smoothly morph. I've also got a kind of ambition here to, yeah, map it to a circle instead. Okay, we can do this. This is fine. Let me see if I've got a saved thing for the projection, because projection's easy. So we've got F, which I don't mind. Let's edit F. Yeah, okay, so concept is going to be semicircle is mapping to somewhere in the fairy diagram, but then translation happens and it's mapping somewhere else. So we have a slider for the amount of translation, which should really be an integer, but we get to visualize, depending on where we initially put the semicircle, as you change the slider, different stuff will happen. And the function is going to be something like, with a slider in it somewhere, the function is something like move it away from the circle to the upper half plane model, translate it, and then move back. I think we know the format of that is something with a parameter n in there. This is sort of like solving Bazoo again, so maybe I should just solve some Bazoo stuff to find a family of these things. I don't know, I'm talking a lot and not doing any Desmos. 10 minutes on the clock, let's go. Okay, so first up, I'd like a map that sends the... at the moment things maybe go to infinity, which is a bit awkward. I've started to think that this translation will look cool if it's on a circle. So, what do I want to do here then? So I need a map that sends, I've done this before, I'm trying to remember how I did it, a map that sends 1 to 1, -1 to -1, infinity to 1. So infinity to 1 is the easy bit. That says that it's something like this. 1 to 1 says something like, oh no, infinity to 1, what am I talking about? Infinity to 1 says that it's something like z plus I don't know divided by z plus I don't know. I would like, I don't want anything on the real line to go to, so I try to map it to a circle. Yeah, so I could do some sort of just easing. I'm not sure if these are the right numbers or how I should I control the numbers all at the same time? Should they remain mathematically related somehow? There's different ways to do this. I know 3 blue 1 brown does a bit of both, that sometimes those transformations are preserving some quantity and doing something gorgeous, and sometimes there's a package that they wrote which just moves things to where they need to be. Yeah, which is going to look really good if we get it working, is the only thing I've got. It's going to be like, you're going to be looking at a circle, and everything within the circle is going to be sort of rearranging in an endless loop. It's going to go, whoa. It's going to be really good towards a kind of weird direction. Mathstudio has put a Desmos link in chat roughly a second after I said whoa, which probably means that they've got it working already. I'm the ideas person, right? This is maybe sort of it, but in the upper half plane model. So I think I need the ingredient of where things go to infinity in this one. Right, okay. I can do this. Maybe I can't do this. No, I can do this. Definitely have the projection thing from before, right? Fairy diagram, no. I've got some fairy diagrams. I've got some tones. I do not have a map to the unit circle. Maybe I didn't save it. Always save your work. Yeah, it is sort of modular form shape stuff, aren't we? Bit paper. So bit paper, we want 1 to 1, 0 to -1, minus I. Yeah, we've definitely done this map before. So it's like minus I, 1, Z, Z. See what happens, because that sends 0 to minus I. It sends 1 to who knows where. It sends infinity to plus I. I put I up here. Oh, bother. Why am I struggling so much with this? about it is making me really, really bad. I don't want to send anything to infinity, do I? If I'm sending the real line to here, or maybe I'm sending minus I or something to infinity. Definitely shouldn't be sending a real number to there, so I'm going to put an I down here instead. Oh, I've had this before. Something like this anyway. This is sending I to infinity. It's sending 0 to minus I. It's sending 1 to looking pretty good. 1 minus I over 1 plus I. Minus sign here as well. So I'm still sending 0 to minus I. I'm still sending minus I to infinity. And now I'm sending 1 to something sensible like minus 1. Minus 1 to something sensible-ish like 1. So more or less, drop the minus sign, see what happens. Okay, this map. See what this map does. I'm running out of time. Z plus I. I've never seen a map like this before. I Z plus 1. G of T like this. Perfect, looking good. That looks like a unit circle to me. So G of 0 is up there, which is a bit weird. G of 1 is over there. 2, 3, it's going to have infinity down there. And it's going to have minus infinity over there. What's it doing for G of, if I add I to both of these? I was really unhappy with that, isn't it? If I add I, is it going, sending the upper plane to, oh, it's sending the upper plane to the outside. So flip this. 1 over Z afterwards, which would be 1 the other way around. So now it's sending, that's good. It's also sending infinity to the top now, which is nice. And if I add a little bit of I, add a little bit of I, not O, I, a little bit between norm 1 or something. Let's just add a little bit. It's going to the inside of the circle as I add I. So that's a good map. I like that map. I sort of want the inverse of that map as well. Inverse of that map. Yeah, inverse of that map. Yeah, thank you. thank you chat. We're playing along with minus signs and I's. I'm in some sort of like locked in mode now. Here we go. Inverse of that map, I think, is the inverse matrix, probably. So let's quickly calculate the inverse of the matrix I1, 1I, which has determinant -2. So probably the inverse of this matrix. How do you do inverses? Minus I, minus 2, yeah. Put minus signs everywhere. Something like I1, 1I. So if I do new function, which is some sort of related thing that is possibly the inverse of that function, possibly not. Let's try it out and see what happens. IZ, oh, this can't be right. Currently got something that's basically the same matrix. Like exactly the same matrix. What are we supposed to do? You're supposed to flip those minus signs here. And also here. And maybe divide by 2, let's find out. So that's a good start. That's pretty good, isn't it? That looks like the could be the line y equals x. Seems good that h might be the inverse of g right now. Let's put in some -3 and 3 or something. Oh, it's not happy with some of these negative numbers, but that's fine with me. Because all I really want to do is do a sort of compound function where I map points in the circle. I can't see any of them yet, but points inside the circle. I want to send them to the so P for points. Send them to the let's type some points in the unit circle. Send them to the real line. Add n, and then send them back. This is the kind of transformation that I want to do. where n, unfortunately, is going to be some sort of slider. So what do I want here? This plus this I. So that's some sort of point. Hasn't come back to this somewhere inside the unit circle, so I'm quite sad. But, you know, we're trying. So why's that happened? What's h of p? Some horrible number down here. H is sending things upside down. H needs a minus sign. Also flipping the plane. That looks good. So, okay, better. H is now somewhere upstairs. We're translating by adding a real number to it, and G brings it back. So I just want some more like scattered points inside the circle. At the moment, I'll just have random points. Next task will be to choose sensible points to illustrate the kind of fairy circle inside by drawing loads of semicircles inside or something like that that are just mapping beautifully to themselves. We're going to be inside a unit circle, so just to put that in first. So we've got already the points P, which I've got this purple point is coming in for this one. Let's throw in some more points. What do I think? 1.3 plus 1.4i. So you see that one starts. Oh, that's pretty bad. That's going that way, and that one's going that way. That seems pretty unlikely. With some sort of like weird animation. Ooh, maybe. No, I don't like this. They're no longer inverses of each other. Bother. It's not sending them back correctly. Okay, so I messed this up at some point, didn't I? I put minus signs on it. Did I put the minus signs on wrong? Maybe. Yeah, I've really messed that up now. Quick test. GF. See, that looks nice. For reals, it's sending reals back to itself. I should have checked that it was doing anything sensible for other points, and it's not. So I've only got the real line correct. This is great fun. I'm enjoying this. Right, quick sanity check at the moment that G currently maps the reals to the unit circle. It looks like it maybe does. If I make that large, it's going up. So I make this. So G is the function of my dreams. It's doing the correct thing. It's mapping the reals to the outside of the unit circle, and also just to check, it's mapping the positive half bit to interesting points inside the unit circle. As I change that imaginary part. We're going slightly long today. Here we go. It's chill maths. Hopefully infinity is going to infinity, or something outside the circle, like in G's case it's minus I. Oh, that doesn't seem good. Oh, but G maps the reals. Wait, if I sequence my functions wrong, G maps the reals. G maps the upper half plane back to the circle. Yeah, that's good. This is the dream that we get this working for n between 0 and 1. Translation in the upper half plane, because I think all of these transformations relate back to a translation in the end. Maybe not. Maybe not. How do you want to illustrate this in the upper half plane? Yeah. So you're calculating the inverse for me. I don't know. You just saw me try to calculate an inverse and it went dramatically wrong. For example, if I calculate this, it's currently giving me some random points over there, and I would like it if h was sending the function h sent the unit circle to not this, but less I flavoured, like the real line, please. So I'm going to try and fix that by making h a more accurate inverse for g. Have another go at calculating that. So I currently have iz plus 1, it's just a linear function. How hard can it be? Equals u, and I just want to invert that. So I write down something like an equation for what I've currently got with a plus 1 in it. uz plus ui. And I'm going to rearrange that for z. So I should get something like z equals, right? So I minus u. Z equals ui minus 1. So z is ui minus 1 over I minus u is probably the thing that's in chat, isn't it? So this should be an I over here, and ui minus 1. There you go, now it's back in the reals to the reals. There is a plus or minus sign because I would like to know whether this is going to the upper half plane. Yes, it is. Good. Okay, so H now sends points from the unit disk to the upper half plane. That's good. Okay, happy with these. So hopefully if I take points in the disk, I could send them to the upper half plane, add a number to them, and then send them back again and see what happens. That's the dream. So we've got points P, and at the moment, yes, they're mapping back to themselves again. The green is the images are the same. But if I animate N, they go along their merry ways to whatever their destinations are. Okay. So, time to make P into an absolutely almighty list of points, or possibly parametric stuff, because I believe that it will interpret this for us if we ask very nicely for a parameter T. Not sure. Maybe it'll panic if there's a whole list of things involving T. So, yeah, something like, I would ideally like to have a circle, like an equation for a circle that's orthogonal to this one, and just track points on the equation. It can calculate them by taking points in the complex plane and saying, are you on that circle? The image of the circle, i.e., if I follow the functions back again, do you satisfy some equation? So if I have, for example, the circle x squared, or maybe let's even go for a complex number, z minus 1 plus I squared equals 2 or something. That's huge. Mod signs. Desmos is going to be willing, I think, to calculate this. Oh, I've messed up my mod signs. Now it's angry with me. No, I want to close the mod sign. There we go. Unhappy? Implicit equations of x and y. That's annoying. That's no fun at all. So I cannot have a circle written in complex numbers. That might be a sign to stop. Yeah, I want lots of circles though. So I'm worried. Oh, if you put x plus y, it's happy. Oh, that would be nice. It was not a sign to stop. Okay, that circle's not orthogonal to the one I've currently got, but kind of plan is something like instead of x plus iy, we write something like, let's get this right. No, let's just guess. G of h of x plus iy plus n minus I plus 1 mod sign equals 2. So that's something mad. So this starts off as this circle, and then as you change the parameter, stuff moves or whatever. I don't know. I think it might be moving the wrong way. I possibly want that the other way around. That looks a bit better. Different colour. So as you change the parameter n, it's moving, and like how the green point and the blue point on the boundary are moving, if this yellow circle moving, kind of everything's moving over there. That's kind of interesting. Translation. Is a translation just a rotation of this picture? Am I putting loads of effort into rotating a circle? No, that inside green point is not just rotating. So this is going to let me find images of circles, so long as I can define the circles. This is daft, isn't it? I should just do the whole thing in the upper half plane and then project it at the end. Probably. We found it really hard in the past to draw all of the circles. But then I suppose, yeah, okay. Maybe let's leave this for another day. But what I'd like is something like all of the circles in the upper half, all the semicircles in the upper half plane model, apply this function g to those points plus some number n. So first add n, forget about h, first add n, and then apply this function g, and I'll take all of my shifting translating semicircles and plonk them into the circle. So we'll get some sort of fundamental transformation of the fairy diagram where everything smoothly moves inwards, and it will show loads of semicircles. But I shouldn't calculate the circles in the circle model because that's really hard. I should calculate them in the upper half plane model where they just connect fractions. We had this before. Can I just copy this? We had these midpoints, and do we have radiuses? Yeah, I'm copying some lines from the other Desmos. How do I feel about this? No, I shouldn't just copy paste from Maths 22222, right? I should understand what I'm doing. Yeah, why not? So we've got this M1, and we've got this R1. Because we're trying to do M1 plus R1 RIT, up to pi, and number 3. I believe that does 3 levels of something. Yeah, okay, so there's loads of the semicircles. Thanks, Math222, I've copied your code. And I actually want to do G of these. There we go. Not bad. Plus some number n. Oh, I've got pasting. So then as I change n, it should get rid of this yellow circle, get rid of this green circle. As I change this number n, it should do some translation in the half plane, which I've also mapped in here. My computer does not enjoy that. Yeah, this is going to be perfect. This is going to be so good. Did you see it all move? Loads of stuff moved, but then it ended up with lines everywhere it originally had lines. It's doing a kind of rotation, but also deformation. And I think if we do this just right, this is just one sort of transformation. We're never going to smoothly animate a reflection sort of thing, are we? But if we do this just right, then maybe my computer's already not happy with 3 levels on this, and I probably want quite a lot more in order to get this top stuff. Maybe some vertical lines as well, the ones that connect to infinity, so that I get these points that go all the way up here. Possibly different filtering on which points we look at. I think we currently have a range. Then we're visualizing one of these. It's a translation in upper half plane, but in the circle model, where it feels a bit more like a binary tree in the circle model, and there's no infinity to worry about. Things are doing this weird. Yeah, it's really jerky. Can I slow motion this? Give my computer a chance. Okay, slow mo, let's try. There we go, okay. How much do I want to do this? It's quite good. This is quite good. Yeah, move all the circles around. And right, this is like a pivot at infinity or something. So the infinity point is staying still because the point up here is mapped to infinity and then translates to infinity and then comes back again. So that point's staying still, and it should have loads of lines coming out to all of the points labelled with integers. We need those vertical lines because those are the ones that are spiralling around. So I should probably have, how am I going to do that? Not sure. So how about G of, so several integers, those are the points, brilliant. You get to see them live if you do this in Desmos. Several integers plus IT, and we're also adding this translation n. Good, and I'll send T, they should be really tall lines, so send that up to like 100 or something. Lovely, and that's the end of the translation. Let's play the translation again. So yeah, okay, so we get this pivot infinity, where that's moving around. We've got all these lines coming up from infinity, and we're moving around to look at the next one. Pivot. That's going to end up looking like it did at the start of the animation, with a line coming straight down the middle. Which doesn't quite, yeah, it was sort of okay. They should be green as well. And unfortunately, because I've not got very many, because 3 is a small number, you can see the asymmetry at the end. It should still be symmetrical. It should look the same as it was. It's a symmetry of the fairy diagram. So ideally these would be green. Let's just change that and see if we can wrap the number 3. That's the number of levels, and this 3 is the kind of number of these spikes going out to infinity, which is kind of important for this one. Yeah, I think that's what I'm going to do today. It's 4:15. Let's call it there. This is just one sort of symmetry, which is preserving this point at the top. Pivot about infinity. We're going to save it because it sometimes crashes. So it's going to be pivot about infinity. Let's spell. Spelling. Link in chat. If you want to make that better, or just watch the weird animation, but you could probably watch it more smoothly at home because your computer is not trying to also stream to Twitch at the same time. After the stream finishes, I'm going to play that and it'll be lovely and smooth. Right. But I think we're going to call Transformations of the Fairy Diagram, call it there. Thank you for joining in with Chill Maths. Thanks for taking part in continued fraction symmetry stuff. Next time, possibly. Am I here next week? I think I probably am. Yeah, I'm here next week. My calendar just says paint the front room, so we'll see if I can paint the front room around the stream. And have a nice weekend. Have a nice everything else. I will see you next week. Wait, no, that's the official sign off for work purposes. See you whenever. Have fun. Thanks for all the tea. Bye. Right, I'm ending the live stream. Good to meet you, Honeycat. Nice to see you on the stream. Right, okay. Herb told me how to end this thing. I have to say, I'm ending the live stream. And then press that button.